Okay, good day. In this recording, we will talk about one electrostatics problem, which is the following. So suppose that we have a sphere and the upper half is kept at potential V0 and the lower half is kept at potential minus V0. Okay, and suppose that we want to determine the potential outside of this sphere. Okay, so another technique to do this is to use, because of azimuthal symmetry, I can write the potential outside, for example, in the form L equals 0 to infinity, AL over RL plus 1, PL cosine theta. Okay, so that's actually the form of my potential. Okay, and what I want is to determine the coefficients so that on the surface of the sphere, and sorry, I didn't give the sphere a radius, so let's make that capital R, okay? So I want this potential to give me the specified potential on the sphere. Okay, and to do that, what you can do is the following. You can you use the Fourier trick actually, because the Fourier trick for this particular orthogonal function, the Legendre polynomial. Okay, so the next step would be to say, okay, I'm going to say L equals 0 to infinity, AL divided by R, L plus 1. And I'm going to integrate from 0 to pi on this side, PL cosine theta, PL prime cosine theta, sine theta, d theta. Okay, and on the other side, my integral is going to look a little bit different, because on the other side, my integral is 0 to pi over 2 PL prime cosine theta sine theta d theta V0, okay, minus V0 pi over 2 to pi PL prime cosine theta sine theta d theta. Okay, now we should finish this first. We're going to, of course, use the orthogonality relation for Legendre polynomials, which goes like this. We could switch to another variable, cosine theta, in which case dx is negative sine theta d theta. Okay, so we can do that, and then actually minus 1 to 1 plx PL prime x dx is equal to 2 over 2L plus 1 delta L L prime. So we can use that relation to extract from this the coefficient L prime. So in other words, what we're going to have on the left side is AL prime over R to the L prime plus 1, and then 2 over 2L prime plus 1. And this is equal to this second integral. Okay, the question now is, how do we deal with this second integral? Okay, and so I'm going to actually write this so that first of all there's going to be a V0. Okay, but how do we deal with the second integral? That's the next question. And the answer is, first of all, we should realize that Legendre polynomials are odd or even, depending on whether L is odd or even. Okay, so the first thing we can say is that, well, if the Legendre polynomial is an even function, then the V0 and the minus V0 parts will cancel. So first of all, we're only going to have odd components. And the other thing that we can say about the odd component is that if I integrate, for example, this one from 0 to pi over 2, I'm going to get the same contribution from the other side. So basically, I can write here 2v0, 0 to pi over 2. That's a reasonable way to write it. And PL prime cosine theta sine theta d theta. But I already introduced this other variable, x. So let me actually reconvert everything. So this is actually going to be 2v0 integral PL prime x dx. And the integral will go from, it goes from 0 to pi over 2. Actually, it goes from 1 to 0 or minus 0 to 1. Okay, so this is, and now we need to worry about this. So I will actually solve this for the first few L primes. But one way we can actually proceed is to say that PLX is actually 1 over 2 to the L factorial dx to the L x squared minus 1 to the power L. So this actually is the Rodriguez formula, which gives the gives the Legendre polynomials. And actually, to start with, for example, I can actually put this in here and integrate it. Okay, so in other words, if I put this formula, I'm going into this, I will have minus 2v0 over 2 to the L. Let me say I suppress the prime because it's just easier. So I'm not going to indicate prime. So this is actually a L over R to the L plus 1, 2 over 2 L plus 1. There's a lot of bookkeeping here. 2v0, 2L factorial. And when I put this in that integral, what I'm going to have is dl minus 1 x squared minus 1 to the L dx L minus 1. And this goes from 0 to 1. Okay, and then, for example, I can make L equal to 1. Okay, then I have x squared minus 1, but I have the 0th derivative of that, right? So I have the 0th derivative of that. And so it's also the function itself. And I have it from 0 to 1, okay? So I'm going to have a minus 1, I guess, because 1 minus 1 is 0, 0 minus 1 is minus 1. So my first, so A1 over R squared 2 over 3, right, is equal to, the 2 cancels, the minuses cancel, V0, I guess it's, yeah, 2 to the L is 1, so that's all 1. No, that's not 1, that's 2, but that 2, it cancels with that 2. Okay, so that gives us a 1. Okay, and then we can proceed similarly, and we've already established that only odd L's are needed. So the next one would be L equals 3, and we would have to take the second derivative of that, and so forth. So this is actually one way of solving this problem.